Friends, my name is Yashas and today we are gonna learn about contour bunds. In this video, we're gonna talk about the concept of contour bund and how to design the contour bunds. Contour bund involves the construction of narrow-based trapezoidal bunds. Narrow-based means the base of this trapezoidal bund would be as less as possible because we want to save the agricultural lands, because while making this bund we cannot produce crop on the bunds, we cannot plant the crops on the bund, and these trapezoidal narrow based bunds are placed on contour lines for the purpose to reduce the runoff velocity so as they could increase the infiltration rate. This would be the area where the water would be standing and it would be able to infiltrate into the soil as it would get more time. These are generally recommended for the area having low rainfall that would be less than 700 nanometer. It is usually constructed on a land having 2 to 6% slope. The contour bunds are the series of bunds divide the area into strips. This would be dividing the area into strips so we can check the flow of water. These are aligned in this direction, like the slope is coming down, so that would be aligned in perpendicular to the direction of the slope so as we can reduce the velocity and the amount of the water. And of course, when we decrease the velocity and amount of the water, then it would lead to decrease in erosion rate, and when we hamper the flow of water, it would also increase the infiltration rate and recharge the groundwater. So now we're going to talk about the design of contour bunds. While designing a contour bunds, we need information on rainfall, slope, soil texture and soil depth. This is also based upon the soil type, as there are different soil textures that would be clay soil, sandy soil and loamy soil, and for making this stable cross section we're gonna talk this about in ahead slides, that what kind of slope we require for all this different kind of soil. And for designing the contour bund, we need to calculate the vertical and horizontal intervals, and then we have to determine the cross section area. The cross section area includes the base width, top width and the bund height. So let's talk about what is vertical interval. The vertical interval is the distance between two successive bunds, that would be between any two successive. So to calculate the vertical interval, we can take any two successive points that could be from upstream slope. This would be distance, would be vertical interval. We can also take the downstream toe, this, and we can get vertical interval too in this type too, from downstream, or we can also take the midpoint, and from this we can also calculate the horizontal interval. The horizontal interval is the distance between two successive bunds in horizontal direction. That would be this two, depending on which toe we are taking, we can calculate the horizontal distance too. From upstream, this would be horizontal distance, and if we are taking from downstream or from the midpoint, then too we can also calculate the horizontal interval. This horizontal interval and vertical interval represent the spacing between the bund, as we just saw. Now we are going to talk about the bund height. So the bund height should be sufficient to store the expected runoff from a rainfall event that have occurring 10 years, event having 10 years recurring interval. The bund height include the calculated depth of water corresponding to the 10-year recurrence interval runoff and a freeboard. This freeboard is provided to avoid the overflow. This, as we can see, like this is, suppose this is our bund, and in this the total height would be capital H. So we can say that the small h would be the depth of water. This we are going to calculate theoretically, and but there could be overflow too, so we just suppose is 25% to be freeboard. We take 25% as a freeboard, and this both, when we add up, we get the total height of the bund. The bund design also include the estimated of contour length per hectare of the land, which help in estimation of the total earthwork and the cost of the contour bund. This means, of course, this height we just calculated would be required to calculate the earthwork and cost of the contour bunds. Of course, in this we can also add the area lost due to making of contour bund, but currently we are just going to talk about the cost of the contour bund that would be implied in constructing this contour bund. Now, to design the contour bund, we also need to know about the side slope. So, as I earlier mentioned, if it is a clay particle, then the slope would be much, so we can make the slope much stiffer, because as we know that the soil aggregate can stay together betterly than the sandy particle. So in sand, the trapezoid would be a lot more flat curve would be there in terms of trapezoid. And when we talk about the side slope, we consider the horizontal distance, that would be h by v, to calculate the side slope, and that would have different values depending on the type of the soil. For clay soil, it would be 1:1, the horizontal and vertical. For loamy soil, it would be 1.5:1, and for sandy, it would be 2:1. Means in case of sandy, the slope would be much more flat, and in clay, the slope would be much more stiff curve than that. So to calculate vertical interval, there is one general formula, that is Vi is equals to capital S divided by A plus B. In this, vertical height is only dependent upon S, and A and B are our constant, and this to depend upon the rainfall magnitude of a place. In case of heavy rainfall area, A could be 1/10 and B is 60, and in case of low rainfall area, it would be 1/15 and B would be equal to 60, and in case of heavy rainfall area, it would be 1/10 and B would be 60. This both are empirical formula, and these are already put together by the scientists, calculated by experiments, and from this formula we are going to get values that would be in centimeter of our vertical interval. One scientist, Ramsar, also proposed the following relationship to estimate the vertical interval, that would be vertical interval is equals to 0.3 bracket s divided by 3 plus 2. In this, s is slope, and that would be in degree, and vertical interval would become in meters. And this also depends upon when we calculate this, then vertical interval for different types of soil. For soil having high infiltration rate and permeability and good conservation practices, we will be increasing the vertical interval by 25%. And for soil having low infiltration rate or permeability, and particularly when used with unfavorable cropping condition, the vertical interval would be decreased by 15%. This would be the most popular one given by Cox. This is the most widely used to calculate the vertical interval. In this, the vertical interval is equals to 0.3 into x into s plus y. In this, the vertical interval would be also calculated into meters, same as Ramsar, but the slope would be in degree. the slope would be in percentage, and the x and y are the factors that would depend upon rainfall and infiltration rate and crop cover. The x is defined as rainfall factor and y is defined as infiltration rate and crop cover, and these values are already determined experimentally, and that we can see in the following table. For the values of x, the rainfall distribution could be like scanty, so the rainfall would be less or equal to 640 mm, and for that the value of x would be 0.8. For moderate rainfall, that would be 640 to 900 mm, the value of x is given as 0.6, and for heavy rainfall that would be greater than 900 mm, the value of x is given as 0.4. Now the y depend on two factors, that would be the intake rate and the crop cover. That would be intake rate is infiltration rate or permeability, and the crop cover during the erosive period of this whole rainfall time. Now if the infiltration rate is below average and the crop cover is also low, then the value of y would be 1, and if the intake rate or infiltration rate is average or above and the crop cover is also good, then the value of y would be 2. And if either the intake rate is below average and the crop cover is good, or we can say that the average infiltration rate or above infiltration rate with low crop cover, means this crisscross, then it would be equal to 1.5, the value of y. Now we're gonna talk about how to calculate the horizontal interval. And the horizontal interval mainly depends upon the slope and is calculated after we have calculated the vertical interval. So the horizontal interval would be equal to the vertical interval divided by s into 100. In this, the value of s is taken into centimeters, and the value of hi would be in the same unit as the vertical interval. After we have calculated the vertical and horizontal intervals, we can calculate the bund cross section. But before we calculate the bund cross section, we also need to know about the height of the bund. The height of the bund is based upon the amount of water that need to be stored behind the bund. So there is also a derivation for it. So firstly, we're going to talk about this diagram. In this, the hi is horizontal interval, vi would be vertical interval, w would be the width of the water spread, h would be the height of the bund, and this is the stored water, and this is the distance between two bunds, and this is the stored water behind this bund. So from above figure we can see that these two triangles are similar, so from based on the principle of similar triangle, we can say that w divided by horizontal interval would be equal to h divided by vertical interval, and when we rewrite it, it would be the width would be equal to the horizontal interval into height divided by vertical interval. Now if we talk about the amount of water that can be stored behind the bund, so as we can see, this is the triangle, and the amount of water that is stored in this would be half height into base, so that would be half h into the w. And as we already found what is the value of w, from this we can put into the formula, and we would get the amount of water stored behind the bund would be equal to half into h square into vertical interval divided by horizontal interval divided by vertical interval. Now we're going to talk about what would be the required volume of water that need to be stored. So supposing that the amount of 24-hour excess rainfall that needs to be stored is RE in meters, then the amount of water retained behind the bund per unit length would be equal to RE into horizontal interval into 1. That would be 1 is the perpendicular to the board. Now we're going to talk about the cross section. Cross section is generally simple because our shape of the bund is trapezoid. So for trapezoid, the cross section area would be equal to the base plus top width divided by 2 into the height. This would be the base width and this would be the top width, and when we add this and divide it by 2 and into with the height, then we will get the area or the cross section area of the bund. And by the thumb rule, it been estimated by scientists that under Indian condition, the top width and the bottom width are typically fixed as 0.5 meter and 0.2 meter. However, for stability, the cross section area would be the minimum cross section area should be of 1 square meters. And of course, it is less than 1 square meter, then it has several demerits that would be a part of different discussion. So some other dimension could be length of the bund per hectare of the land. So the length of the bund per hectare land would be 10,000 divided by horizontal distance. So as we know that 1 hectare is equals to 10,000 meters, so that we are dividing by horizontal interval. So we will get the length of the bund per hectare of the land in meters. And we have already talked about what is HI, that is equals to 100 VI divided by S slope. And by putting this into the above equation, we can get L is equals to 100 into S divided by vertical interval slope. Now we're going to talk about the earthwork required and the area lost. Due to this formation of the bund, we lost the area. We are also going to talk about that. And the earthwork for bunding include the main bund. This would be our main bund. The side bund. The side bund, the side bund would be only this small, and the lateral bund would be this whole. This is the side bund, and this would be the lateral bund, the whole portion. And all these bunds may be of same cross section area for the ease of the calculation, but may be of different cross section area too. Now to calculate all this, the length of the side and lateral bund may be assumed as 30% of the length of the contour bund. From the above equation that I found that the length of the contour bund per hectare would be equal to L is equals to 100 into S divided by vertical interval. So when we add 30% of this to this whole, we will get 130 S divided by vertical interval. That would be the total length of the bund per hectare. Now we have calculated the total length of the bund per hectare, and when we multiply it with the cross section area, we get the total earthwork. Now to calculate the area lost under the contour bund, we can calculate it by multiplying the length of the contour bund per hectare with the base width. That would be AL is equals to 100 into S divided by vertical interval into base width. B is base width here of the contour bund. That would be this base width. We are taking this because when we make the contour bund, then we lost this much space or this much land due to formation of the contour bund. Like the earthwork calculation, we need to add 30% of the area lost calculated from above to get the total area lost, considering the side and lateral bund. So this would become, when we add 30% to it, it would become 130s into b divided by vi. Now, after calculating the earthwork and the area lost, we can talk about how to align this all and construct the control bunds. For alignment and construction of the control bund, we firstly need the plan or the map of the area. The map of the area, currently we are the mapping the whole area and finding the control line with the means of satellite data and GIS software. But in olden days it was prepared by plain table survey if in case the map of the area was not available, and in that whole all the natural features like streams, gullies and field boundaries would be shown. The area of the map is divided into blocks of suitable size, and these blocks, the location of the control point are marked. Currently we use the direct control method, in that we already know the control lines and we just put the bunds on those control lines starting from the ridge line of the area. For the alignment, the first one is directly located in the field, and after that the field is smoothened to avoid undesirable surface irregularities, and the position of the second and subsequent bunds is then marked as per the plan. Thank you. That would be it.